Okay, so today we're gonna. Uh, Last time we started the discussion of non-abelian gauge theory, and today we're gonna start the quantization of the theory. But as usual, I start with a review of what we discussed last time, and if there are any questions that come up, please do ask. So, um, in search of four-dimensional interacting quantum field theories, we turn to gauge theories. U1 gauge theory, and in general, abelian gauge theories, are the U1 gauge theory is the theory of photons. They do not self-interact. It's a free theory. We quantize it in QFT1. And to get something non-trivial, we included charged fermions. Um, Such a theory that describes fermions coupled to U1 gauge theory is called QED, right? So the only interaction in this theory is this vertex. This is the only thing we've got. And we saw that in four dimensions, this interaction is irrelevant. And the theory doesn't exist deep in the theory is trivial in the infrared. There's no interaction deep in the infrared. In the UV, the theory is sick and it has a Landau pole. All right. So what about non-abelian gauge theories? So one thing that's very different about non-abelian gauge theories is that the theory is, as we saw last time, self-interacting. So you don't necessarily need to couple it to charged matter to get something non-trivial. And we're going to start with that. Although to describe nature in Santa Wall of particle physics, we're going to see we're going to have fermions charged under a non-abelian gauge group theory. All right, questions so far? A little bit of review of the gauge theory, the geometric picture. So you have the space-time manifold that I'm denoting by M. At each point, you have the internal field manifold. The field is a map from space-time to a point on this field manifold. That's what the field is formally. So we often take this internal manifold to be a Lie group, right? For example, it could be U1 or S1. We talked about principal bundle last time, but I don't want to get into those the details all that much. I'm going to describe a simplified version where, for example, this could be S1, it could be SU2, which is topological, which is locally the same as S3, right? It's a double cover of it. Hopefully you recall that. It could be UN, SUN, or SON. Primarily, we're going to be concerned with SUN theories. So the group acts so there's some sort of a charged matter fields phi I that are in the fundamental of SUN, for example, and the group acts by left action, right? So we're looking at, for example, unitary representation of the group acting this way. But then, as opposed to the case of global charges, global symmetry, we said we're going to just promote this to a local transformation. So we're going to act with the group elements at different group elements at different points. So this is now the group element could depend on the point where you're inserting. For instance, your psi of x, let's say this is a complex charge scalar under some U1 gauge theory, or it could be a fermion. Under this transformation of U1 is acted on by e to the power of I alpha of x, psi of x. Gauge transformations, these are gauge transformations, are unphysical. So these UIJXs are not observables. And in fact, one way to think about it is, so in this example of U1 gauge theory, what you have in mind is here's your space-time. At every point, you have some sort of a U1. So let's just simplify it and pretend M is just one-dimensional. So here's your M, right? You have the fiber at every point, which is S1, right? So these U's of X, which are different rotations, you could, you would act with different rotation at different points in space. time, and those are considered gauge transformation. That's unphysical. So, for example, some sort of we talked about a section, some sort of a configuration like this could be trivialized by bringing these guys down to the same point, you know, by applying different u of x's at different points. But the point being that this this statement is doable only if there is no non-trivial topology, right? So if you have, say, if the space time, this is if the M is a circle, right? So at every point you have a S1. What is the fiber bundle in this case? S1 times S1. What is it called? It's a torus, right? So in torus, you have a torus, and you could have a field that is a section of the torus, which is topologically trivial. At every point, you could just bring this down, right? Or you could have some field configuration that is twisted. It goes around and comes back. It loops around once, right? Then using gauge transformations, you cannot trivialize that transformation, right? So that is going to be something physical. All right. So we introduced the notion of a connection. We said that to define a derivative, in the action for these charged matter, we would like to have a derivative, right? But we saw that to have a derivative, we should have a way of comparing the vectors at this point in the internal manifold to vectors at that point, right? In principle, so what you would like to say is that you would like to identify a vector here with a vector here as no change, right? Like you want to say this is the same vector. The rule that decides that's the same vector is called a parallel transport, right? So when you identify this point to that point, you could use some sort of there's some sort of an object that has two indices. One index is acted on the left by the group. The other index is acted on the right by the group. And this is non-local because it depends on 2 points, right? And by taking the limit of these 2 points colliding, you can define a covariant derivative, which is a rule for parallel transport. It's just saying that what point is equal to what point, right? Now, when you take this W, this object, this bilocal, that transforms on the left and right using the group at different points. When you linearize it to the first order, what you obtain is a connection. It's a gauge field. So the connection is a rule for defining for carrying the operator along the manifold, right? So dragging some vector field that lives on a fiber along the manifold. Good. Questions? All right. Now, of course, we're going to be taking these manifolds to be Lie groups, right? So, or the representations of the Lie groups. So I'm going to remind you a little bit about Lie groups and Lie algebras. So if you recall, so now think of this as the fiber, right? This is the manifold at every point. It's some Lie group G, right? The tangent to the Lie group is called the Lie algebra. And the Lie algebra will have a bunch of generators that you could view. The Lie algebra is a linear vector space, right? The generators of it, you could pick a basis like this, right? This is a representation. So there are these are matrices, right? IJ are the matrix indices. And then A runs from 1 to the dimensionality of the Lie algebra, right? For example, when your Lie group is SU2, these generators are going to be the generators of the SU2, which there are 3 of them, right? Depending on your representation, it could be matrices of various dimensions. Good. All right. So we're going to pick a particular normalization. This is a normalization where you normalize you want to form an orthonormal basis for your Lie algebra. So here's the orthonormality, orthogonality, and then the normalization. The convention here is half for the fundamental representation. The commutator, every Lie algebra comes with a commutator relation, right? Which has the structure constants of the Lie algebra encoded in it, right? We saw that all the properties of the Lie algebra are basically universally described using the structure constants, right? Now, because as you go from here, from a point to a point, what you have is uh, an infinitesimal transformation on the internal manifold as your one form connection. Therefore, your one form connection is Lie algebra valued. So this gauge field is going to be Lie algebra valued, right? So if I just changed notation already here, these are lambda A's. So in general, you expand your A mu in terms of these generators. Good. For example, if you have SU2, there will be 3 of them, right? X, Y, Z. Sigma X, sigma Y, sigma Z. Good? Questions? Yeah.
So in the Arnold form effect, which is the U1 bundle, even though the space is Euclidean, we still have some the non-contractible. So why is that? Is that because of the magnetic field in the middle is interpreted like
Yeah. So I'm going to comment on that. This is not about the curvature of space-time. This is about the curvature on the bundle. This is the fiber bundle, right? It's about, well, I'm going to comment on that. Yeah, that's important. Any other questions? Okay. So here's a comment regarding curvature. Field strength is the curvature associated to this one form connection. So you have the space time, right? So here's the space time. Let's say it's the well, actually, I was drawing it here, right? The space time, or this is like say a S1 inside space, right? This is a circle here. It's a circle here. And at every point around S1, you're going to have an internal unphysical degree of freedom, right? Now, S1 is locally flat. There's no curvature to be found at all. As a matter of fact, even if you consider the torus is also flat. What is not flat is that, so your gauge field is a section. This guy can loop around, right? It could wrap around this non-trivially. And that is the curvature associated to this one form. It's the curvature associated to the one form, not the space-time at all. The relationship to space-time is the following. So, well, I'm going to comment on this. How is this? Yeah. Everyone's with me? So, when you let me describe the curvature of space-time. When this is now, I just switched to general relativity. So this is space-time, right? Manifold. Space-time manifold is locally flat. At every point, it's like flat space, right? So at every point, you could pick a set of coordinates, right? That we usually call, so the metric is d squared, g mu nu, dx mu, dx mu. But at every point, you could pick a set of an orthonormal basis locally, right? These are we usually write them this way, right? This is the non-coordinate basis. It's a coordinates that locally make your space-time flat, right? Now, this is the structure like a fiber. As you go down, as you move around the manifold, these guys could have a one-form connection. There could be a curvature associated with it, and that's the curvature of the manifold space-time. So here, what is going on is that it's about the metric, which is a tensor, right? That is a fiber that describes this structure here, right? Space-time is about the, well, curvature of space-time is about the metric tensor, right? There are situations where special general relativity is literally a gauge theory. So if you're curious, you could look up Palatini. Ooh, I'm going to misspell this. Palatini formalism of general relativity, where you write down GR as a gauge theory structurally. It's called a first order formalism, blah, blah, blah. So curvature is associated with the fiber bundle, right? The curvature of space-time has to do with the frame that trivializes the metric, right? All right. So the notion of parallel transport is hopefully clear, right? So you have a bunch of vectors, you move them along, right? But now when you have curvature, you end up with holonomy. As you go around, the vector does not end up where you started with, right? So this is probably, this picture I'm drawing is perhaps the source of the confusion, because it seems like I'm talking about space-time curvature. Now, what is curvature fundamentally? Curvature as a local notion is you make a little loop, right? And if under parallel transform, you don't come back as you go around the loop, then you have curvature, right? Now, think of the loop as something like this. This is parallel transport in the mu direction, parallel transport in the nu direction. You go around, right? This is the commutator of d mu, right? How much d mu is different from d mu, right? That is actually the field strength. Field strength is, yeah, to every connection, one form, there's associated field strength. Good. So to make things clear regarding general relativity, think of parallel transport. In general relativity, you do parallel transport to vectors, right? You say that I'm just transforming this vector, right? That's my rule of comparing the local coordinates. Here, what you're transforming is the field value in some internal manifold. Okay. Other questions? It's a lot easier than GR. A lot more simple. What is the gauge group associated with GR if you were to think of the gauge group? What are these? Yeah.
GL.
Diffeomorphisms. Local Lorentz transformations and translation. So local Poincare transformations. Yeah, think about that. That's a beautiful story. There's a simple way to think about GR that way. All right. So we said A mu is not an observable. In U1 gauge theory, F mu nu is. F mu nu is gauge invariant in U1 gauge theory, and it's actually describing B and E, right? The magnetic and electric fields, vectors, right? So it's gauge invariant. Now, if you have a loop, well, I'll draw. If you have a loop like this is this is a bad picture. Imagine you have now space-time is say 3 + 1 dimensions or something. Imagine you have a loop, right, somewhere. It could be on a constant time slice, right? Then if there's flux, magnetic flux going through it, right? You know from the laws of electromagnetism that if you go around this, then the integral of x mu, a mu dx mu is not zero. It's actually equivalent. It's given by the amount of flux that goes through it. How do you know that? What's the origin of what I'm just saying?
Stokes theorem.
Stokes theorem. Precisely. Right? This is Stokes theorem. All right. Good. So then the total, this integral is equal to the total amount of flux going through the surface. Right? Okay. It means that every time f is non-zero, right, you have curvature for this. Like f is a curvature. Now, the physical manifestation of this, these non-local observables, could be viewed can be seen in the Aharonov-Bohm effect. So this loop that I'm talking about in space, to make this physical, think of a particle, a charged particle that you drag along a path and bring it back. Or you could view it as like a double slit experiment, electrons go and recombine. It's exactly like going in two different directions, right? And if they go tracing both paths that have the same distance, right, end up in some sort of an interference pattern here, that's an indication that there has been magnetic field here, right? Because when you turn on the magnetic field, it changes. It acts on the fermions, right? It's a U1 transformation. Good. You can never say there's no meaning associated to that phase at any particular point. The only thing that's physical and meaningful is the integral around the whole thing. That's the only observable. Good.
Does that mean like if you cover up one of the slits in this, you shouldn't see any difference during the magnetic field holding on?
Difference between what? The difference is between the particle, between the two different paths. So if you cover one of them, you just have one path.
Yeah. So you shouldn't see the pattern change if you do that. Whereas, like what we see here is because they're going.
Oh, you're talking about the interference pattern here, of course. Yeah, the interference pattern here is non-trivial when you have both trajectories. Right? When you have both trajectories, then there is interference. Otherwise, there's no interference. If there's no interference, there's no interference, right? Good. This would be a Wilson line. A Wilson line is not gauge invariant. It's only a Wilson loop that's gauge invariant. Right? How does a Wilson line transform? The Wilson line that is from this point to that point in space, under gauge transformation, how does it transform? This is X and Y. I've already said it a couple of times today. It transforms as U of X on the left, U of Y dagger on the right. Right? It's a non-local object. This is called the geometric phase. Now, why is this non-locality? Because the magnetic field anywhere along the path could be zero, and still you would have a non-zero effect because there is magnetic field inside this surface, right? So you could imagine the surface is incredibly large, right? I'm comparing two trajectories that are like light years away, right? At every point as the electron is going along this path, the magnetic field is an electric field is zero. It's the magnetic flux that goes through this whole surface that's non-zero. So it's a form of non-locality. Good. Questions? Because I'm gonna change gears. All right. Now I'm gonna give you, I ran out of time last time. I'm gonna give you a lattice way of thinking about stuff. I've said all along the way that quantum field theory is the continuum limit that there's an alternative way of thinking about quantum field theory from the point of view of a lattice system that undergoes a continuous phase transition, and this is the infrared of it, right? So, what are the class of lattice gauge theory? Sorry, what are the class of lattice theories we have discussed that have given us meaningful quantum field theory so far? What was the lattice example that gave us the Ising model? Sorry, gave us the free scalar field Ising model. What other field theories did we construct? Sorry?
And the rotors.
Yeah, the Roters model that gave us the ON, right? So what is the Rotor? What is the Ising model? You have a lattice, right? At every site, you put up, down binary degree of freedom. The Rotor model is a version where at every site you put a vector that lives on some sphere or some higher dimensional space, right? So that already looks like these were global symmetry setups, right? And then we wrote down an action that was at global symmetry. Now, how do you put gauge theory on a lattice? Is there lattice theory that gives you gauge invariant theories? The idea is very, very simple. Just think about the connection. What is the notion of a connection? So imagine you have a degree of freedom here and a degree of freedom here, right? What is the connection? You have a vector. Let me just draw it as S1. So at this point, you have a vector like this. This is say on a circle. And then you have a degree of freedom like this. Good. You want to say that you want to, it's like synchronization. You want to just have a point of reference. Say this vector that was, so this is sticking in the third direction, right? You want to say this is the same as that. How do you do that? You need a connection. You need an object that is acted on here and acted on here that just moves things, right? It takes phi of I from this point to phi of I at this point, right? So what is it? It's some object that acts like this, x, right? What does this look like? How would you come up with a structure like this? It's a degree of freedom that's not on sites, it's on an edge. That's it. Who said that you have to put the degrees of freedom on vertices? That was an arbitrary rule we started with. You could put degrees of freedom on an edge. That's exactly what a gauge theory is. That's what a one-form connection is, right? Every edge is defined using two endpoints. It's exactly like this guy. It has some inherent non-locality in a sense, right? All right. So now it's exactly like what is so. All right. So let me think of this as a one-dimensional setup. Good. All right. What does it mean to have a non-trivial? So make it one-dimensional, make it a circle. What does it mean to have a non-trivial fiber bundle here? Think of charged matter, right? Like, so these are some sort of spinners like this. Now you say that, let's say this is a rotor model, like a U1, so I can rotate them, right? So you say, oh, there's a configuration where, so drawing this poorly. I should be drawing it like this. This is the configuration of the field around here, right? Now, this configuration is gauging equivalent to the previous one because you could locally flip this, and that's trivial, right? How about a configuration? Well, actually, no, that was a bad example. Well, that's actually true. But let's say these are vectors that gradually Sorry. Imagine it becomes like a Mobius strip. If it has a Mobius strip, you can never make a Mobius strip flat. You could try to locally make it, all of them, next to each other flat, but you can never untie it because of a topological obstruction, right? That's a non-trivial section. Anyway, so in lattice gauge theory, what you start with, you could, as I said, you could have a setup where the theory is just pure gauge theory, no charge matter. So in that setup, you just put degrees of freedom on the lattice, right? What does the degree of freedom on the lattice belong to? It's acted on the left by the group and acted on the right by the group. So it transforms in the adjoint representation of the gauge group, of the group, right? So have you ever heard of a toric code? What is the toric code? Toric code is a setup where you take a lattice and you put a Z2 degree of freedom on sides, like qubit degree of freedom on side. It's a Z2 gauge theory. The Hamiltonian that you would write down is going to be, you're just the only thing that's on that. So going around like this, right? That is a non-trivial Wilson loop, right? So here you have a matrix. You have another matrix here of the group, another matrix, another matrix. So you're just going to multiply them and go around the loop. And if that is non-trivial, you say you have some non-trivial curvature, energy density, something physical, right? Now, just think about electromagnetism. What was your local Hamiltonian? What's the Hamiltonian of electromagnetism? Hamiltonian density. You know this, come on. What's the Hamiltonian density of electromagnetism? Half E squared plus B squared, right? What is it in the language of the in the language of the field strength? Not mu nu, right? It's F because it's you're doing decomposition. That's Lagrangian density, right? So it has these terms, right? Which are E squared, and it has these terms, which are B squared, right? It's a particular decomposition you do. All right. Good. So this suggests that what you need to do is you just need to multiply the group going around. So here's the Hamiltonian. You sum over for every plaquette, right? For every plaquette, you're just going to multiply the group elements going around it. Here it is. Sum over all plaquettes, right? And these little curvature terms. So in the interest of time, let me just tell you that this is a very good exercise for you guys to consider, for example, a Z2 gauge theory or a U1 gauge theory, right? A U1 gauge theory with the degree of freedom you put here is a U1 thing. So think of it as e to the power of I, a phase. It depends on a point and depends on it has a vector component, right? Because moving in which direction? Every edge could be represented using one point and one vector also, right? That is what the gauge field is. Because it was the group element that it was the connection one form was the linearization of this rule that dragged this guy to here, right? That's where the connection one form came from. All right, so you just take this. You could write it in terms of like these phases. You learn that this is a cosine, right? And as you take the points near each other, you have to expand this guy. And in fact, you get the Hamiltonian becomes a constant plus half integral of dd of this is space, f alpha beta squared. So you recover the Hamiltonian of electromagnetism this way. So it's nothing really that fancy. The only thing that's changed is that instead of the degrees of freedom being absolutely local, now you put degrees of freedom on edges, right? But it's not that degree of freedom is not physical. What is physical is the loop, right? It's the Wilson loop. All right, the non-abelian version of it, I'll just mention it and we move on, is exactly the same. At every point, you pick a direction that will identify an edge of the lattice. You put a group element here, B, that I'm going to label it as B of X and some vector, right? That is non-abelian. That's a non-abelian gauge theory. Now you write your Hamiltonian as you go around, you're multiplying, and this is in some representation, right? D by D representation. As you multiply around, you're going to get a D by D matrix. So you're going to take a trace of it, right? So here is precisely what the action is. Why is this B minus 1 minus 1? It's just the way you're traversing the loop, right? Just think about these little things. All right. Anyway, so you take this Hamiltonian, you linearize it. There pops out the Hamiltonian that we expected from the non-abelian gauge theory. Good. What is interesting here is that notice that F alpha beta trace of it doesn't pop up. F doesn't pop up. It's F squared that pops up. Right? It's F squared that's physical. All right. Now, because of the fact that non-abelian gauge theory, well, sorry, because of the, well, when F mu, when A, so what is your covariant derivative? Covariant derivative in the gauge, non-abelian gauge theory is matrix valued, right? So this guy is matrix valued. You could view this as del mu identity, right? Plus, say, IG sum A mu A lambda A. These are now matrices, right? These are matrices. Yeah, that's it. So these are matrix valued. So when you compute d mu, of course, this identity piece will cancel. But because now these are matrices, the commutator doesn't vanish, right? So this commutator survives. This is the origin of the fact that you have interactions, right? Because F mu squared, when you calculate F mu squared, you're going to end up with the commutator squared. These are matrices. The commutators don't vanish. Good? Questions? So this was supposed to be the end of the last lecture. Actually, maybe no. Yeah, that was supposed to be the last lecture. So I'm going to pause here. Everything I said so far today is classical physics. Hopefully that's clear, right? Even though I mentioned like Aharonov-Bohm effect, but that was just like, yeah. Good. What we're going to do today and on Thursday is we're going to quantize non-abelian gauge theory. Now there is a set of tricks. I'm going to try to say the trick, repeat it and repeat it and repeat it again. It's just a very simple structure to it. But if you don't pay attention to it, you're going to get lost very quickly, right? It's not conceptually hard, but I'm just going to explain it once. It's called Fadeev Popov. That's what we're going to do today, right? It's a rule for quantizing. It's a method for quantizing non-abelian gauge theory. And the method is all about how to properly keep track of gauge invariance. That's all that there is to it. All right. Notice that there's one thing that's very important. As usual with gauge invariant theories, keep this in mind. The theory has some non-locality, inherent non-locality in it. We are going through we invent unphysical gauge degrees of freedom because we insist on a local description, right? That's exactly what it was classically. Quantum mechanically, when you describe a gauge theory, to insist on quantum mechanical description that's purely local, in addition to the gauge degrees of freedom, which were made up, you have to make up other stuff called ghosts. Again, this is all because you insist on a local description. I'll tell you what the origin of it is. The origin of it, I'll say explicitly where it comes from, but what it is just because the theory has some non-locality and you want to describe it purely local. All right? Good. So what is the Yang-Mills theory? This is pure gauge theory, no charge matter. The action for Yang-Mills is Yang-Mills theory, to be defined, you need a gauge group, G, that we take it to be a Lie group, and a representation, R, right? So in that representation, you have the Lie algebra generators, TAs. So your gauge field connection one form takes the following form. Any questions about the notation? Hopefully it's clear. So A mu is Lie algebra valued. F mu nu is a Lie algebra valued field strength, right? These are all D by D matrices, D being the dimensionality of the representation. Good. So when you take this trace, what pops up in each of these guys, there's a T of A. What pops up after you take this trace is trace of a pair of generators of the Lie algebra. We mentioned that in the normalization and arbitrary representation, I've been calling it lambda T. I just switch around, right? So this is, what do I call it here? T of R. Right? Oh, sorry. No. This was my notation, sorry. T of R delta AB. The T of R is half for say SU2 fundamental, right? So you divide by T of R just to keep track of normalization of that. This minus 1/4, hopefully you know where it comes from, right? All right. This is the Yang-Mills theory. We're going to try to quantize this today. Let's expand the Lagrangian density. It's twice trace, so that minus 1/4, I'm just suppressing for now. There will be just the regular derivative terms, which are Gaussian. There will be a term which has one F mu nu, one piece coming from the derivative. So let me clarify. Sorry. Good. So there is this term, right? This term expanded has del mu a mu. Well, sorry, a mu. Has this, right? And then IG a mu a mu. So every term will have a first order piece and a second order piece. Right? This is the extra non-abelian part that was absent last time. So there are two of these guys. If you pick the contribution from the derivative from both, this is what you get. This is familiar, hopefully, from the, say, U1 gauge theory. Then you can have the piece from this from one, and then this from the other term. This is an interaction. This is a cubic term with one derivative. And then you could have the term which is quadratic, right? It's purely interaction, four guys. Good. So up to the surface term, you write this down this way. That's a good old propagator of the free theory we're dealing with, except that now, what do we have? We have a bunch of these guys. How many of them do you have? Each A mu is Lie algebra value. So how many A mu's do you have? Say A mu is SU2. How many of them do you have? You have 3 of them, right? So this A runs over the dimensionality of the Lie algebra, Lie group, right? And then your propagator is going to be, hopefully this is ugly looking. The propagator is between A mu A nu B, right? This term. And then there are interactions. Good. So now, previously, when we were doing U1 gauge theory, I mentioned there was a Landau gauge, there was a Feynman gauge, and then there was the arc-C gauge, right? So arc-C gauge had this advantage that, so in the arc-C gauge, the propagator is minus I over K squared plus I epsilon, A de mu minus 1 minus C, K mu over K squared. Arc-C gauge is particularly convenient for non-abelian gauge theory. It's just one convenience of it is that every term that comes up C dependent, you should be careful with because it's very likely gauge dependent. So unphysical. Good. All right. So I'm first going to say what the Fadeev Popov is. Then we're going to do it step by step today and next time. Right? All right. What are we going to do? We want to perform a path integral over the space of all gauge field configurations. Call that M tilde. Good. But not all of them are physical. In fact, all the local transformations of them are completely unphysical. So the physical space, the space of physical gauge field configurations is M tilde modded by G, the action of the gauge group, right? So if you want to look at the physical one, it's like doing the path integral over all of them divided by the volume of the group times the volume of a space-time. Explain to me why that is. Think of a simple example. U1, right? If you path integrate over all A mu of x, what have you done which is redundant? For every point in space-time, you're overcounting by the volume of the group, right? So it's the volume, the total overcounting is the volume of the group times the volume of points in space-time, right? Of course, this blows up like crazy, but as usual, path integrals need regulators. Good? All right. This is just to start, to have something in mind. Or I'm going to describe exactly what we're going to do. All right? So what is the Fadeev Popov method? I'm going to describe it in a series of steps. Start with the non-abelian gauge theory, gauge field, A mu of A. A is the index of that runs from 1 to the dimensionality of the group. Okay? Under a gauge transformation, it transforms as A mu of A plus half d mu covariant derivative of lambda of A. Good? This is a transformation. What is a gauge fixing? Previously, in the case of electromagnetism, we saw various gauge fixings where del mu of A mu equals 0, for example, right? Or in principle, it could be del mu of A mu, some arbitrary function of space. In this case, because the gauge field has is a matrix valued, Lie algebra valued, this is some Lie algebra valued function of space. But in general, gauge fixing condition is some, say, linear functional differential operator acting on A of x equals 0. Good? Sometimes it has a derivative, sometimes it doesn't have a derivative, right? Depending on various gauges we pick. The Lorentz gauge, for example, is omega of x equals 0. All right? Okay. So what we do is the following. We split the path integral over all gauge configurations into a path integral over a gauge fixed configuration, which has g of a mu of a equals 0, times an integral over all gauge configurations, gauge transformations. Good? So these are the gauge orbits. If you gauge fix, it's like this. A gauge fix setup is a section, right? And then when you integrate over lambdas, you're integrating over all the local gauge transformations of that. Good? So this part will have some gauge fixing to some gauge lambda. All right? This is step 1. Step 2. So this gauge fixing will have some omega. That's an arbitrary function we pick for gauge fixing. There's no physics associated with omega. In fact, you pick your omega, I pick my omega, they give the same answer. So if we calculate with your omega, and we calculate with my 1 omega and take the average of it, it's still the same physical answer. Therefore, you could average over all omega of x with a Gaussian measure this way. This is just 1. It's identity. This is exactly what we do in RC gauge. We're going to see that when we average over omega of x this way, this gives us the RC gauge, which is equivalent to adding minus 1 over 2c del mu of a to the Lagrangian. And then this integration, when we do it, we're going to see that there will be another piece to the action called the action for ghosts that is absent in the case of QED, but for non-abelian gauge theory, it has to be there. These are the 2 steps. All right? So what do? We first take the path integral over the space of all field configurations, gauge configurations. We gauge fix, split it into an integral over gauge fixed ones and an integral over the orbits. Good? Then for the gauge fixed one, we're going to average with this measure. We can. This whole thing, the advantage of doing this, the intuition that underlies, this is called Fadeev Popov. The intuition is that it gives you a local action to work with. All right, questions? These 2 steps are all that we're going to do. I'm going to do them first in the case of QED, I believe. Yes, I'm going to first do them in the case of QED step by step so that the ghost piece comes up, but you see it doesn't play a role. It goes for the right? So all of this I'm going to do to QED, and then you generalize. All right? Questions? Let me pause here first. All right. Now, let me tell you a little bit about this gauge fixing thing. Before jumping into this is just a statement about functional integration, but I want to remind you because that was the last time we talked functional integrations. This was like QED1, lecture 304. Hopefully recall, if you have a one-dimensional integral of d lambda, Dirac delta function of lambda is 1. Good? Now, if instead of Dirac delta function of lambda, you have Dirac delta function of some function of lambda, g of lambda, the thing that is 1 is an integral of d of lambda, the absolute value of the derivative of it. It's just an identity. This is unfamiliar. You should go back to calculus and look at it. Look it up. All right? Now, next, imagine instead of a single lambda, you have a series of them, a vector of them, a whole bunch of them, right? So now G lambda is a linear equation, right? Some matrix acting on a vector of lambdas is equal to 0, right? So what replaces this is the determinant of the derivatives of G with respect to lambda I. This is G, right? And integrate over here. Why determinant? Because just think of this as you diagonalize, you work in a basis where you have to diagonalize G. So for each of the matrix diagonal elements, you're going to have one factor like this, right? In general, that's just a determinant. In the continuum limit, the vector lambda is replaced by some function of space-time, lambda of x. G of A is replaced by some differential operator acting on A in principle of x, right? And your identity becomes a path integral over all lambda, delta of G of A, determinant of del G del lambda. Good? Now, just to, as a fun thing, why am I doing this? This is some sort of gauge fixing thing, right? I want to, for example, pick A lambda here. The condition that you're doing, you're picking a G A lambda to be del mu of A lambda minus omega. Right? That is your G. When you take a derivative with respect to lambda, this is what you're dealing with, right? This is actually, sorry, covariant derivative. My bad. Covariant derivative. When you take the derivative, this is just going to give you, if this is 1 over E del mu of lambda, half E del squared. So from this choice of gauge, in the case of QED, what you obtain is the determinant of 1 over E del squared. Good. Let me do that slowly again. Well, I'm actually going to do it. I'll do it. I'll do it in a bit. Let me actually, no, sorry. Oops. Why that? So what is this? G of A of lambda. Let me just do it on the board. That's easier. This is our gauge fixing, right? G of A mu is del mu A mu minus omega. If this is not abelian, put an A, right? This has to be equal to 0. Therefore, we put a Dirac delta function of this guy. We're going to see that instead of putting A mu here, we're going to put A mu, a gauge transform version of this, which is A mu plus del mu lambda. Right? So if I do this, this is what I'm going to get. Right? So then what I'm going to get here is del A mu plus, well, there's 1 over E, sorry. This is 1 over E. So I have a minus, I have a plus. Del mu of lambda. Good. Minus omega x. Minus omega. Right? This is my delta of G. What I have to compute is I have to take a derivative, functional derivative with respect to lambda and take a determinant. So if I take a functional derivative variation with respect to lambda, this is the only term that contributes. and it's linear in lambda. Therefore, the coefficient of it is 1 over E del mu, otherwise known as L squared. What do we have to put? We have to put the determinant outside of it. Good. Now, the only thing, so I just did the calculation for QED. The only thing that changes when you do this for non-abelian, this determinant thing for non-abelian, is the gauge transformation. Here, this is covariant derivative. Good. So everything goes through, this becomes covariant derivative. This is del mu, this becomes covariant derivative. What is the difference between the two? Sorry, the covariant derivative without covariant derivative. When it's not covariant derivative, in the case of QED, what you have is a determinant of 1 over E del squared. That's just a constant. It's infinite, but it's a constant. Its gauge is field independent. It comes out of the path integral completely, right? So this game of imposing the gauge and like performing integration over it gives us this gauge independent, this field independent overall constant that we're just going to discard. In the case you have a non-abelian gauge theory, this is field dependent. How so? Because this covariant derivative has a gauge field in it. So you cannot take it out of the path integral. This fact that this guy depends on the field is what's going to give you the ghost. So we're going to go through that. Good? Questions? All right, let me just come here. Good. Here's my path integral. I have a path integral which is integral over dA e to the power of I S A. I'm going to write it as integral over dA d lambda e to the power of I S, say A lambda or A, doesn't matter, because the action is gauge independent. Then I'm going to stick in there this identity thingy. This is just identity. Hopefully we agree on this. Right? This determinant piece, in the case of QED, gave me determinant of 1 over E del squared. That is field independent. I'm just going to take it completely outside the path integral. It sits outside. What am I left with is d over integral over lambda, d of A, that I've switched the order, e to the power of ISA, this delta of GA, right? Which is this guy. Good? Next, what I'm going to do is my step 2, which is, so this is omega of x. Everything I did had an omega of x in it. I'm going to average over omega of x. So this was my path integral. Well, this is what I had so far. Good. I'm going to apply this averaging outside. This is just, again, identity. What it does, of course, this determinant just goes for the right. It's unimportant. This is an overall unimportant constant. D lambda comes out. This is going to be all unimportant. Integral of d of A, e to the power of ISA. This averaging with this will give me the term that I need to get the arc C gauge Lagrangian. So C is the width of my Gaussian for integration. Good. In the arc C gauge, your action looks like this, which means that your propagator is like this. So the 2-point function is minus I k squared plus I epsilon, eta blah, 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 delta AB. Right? The propagator is diagonal in the Lie algebra elements. These are diagonal elements. Good. A W boson along the way is not going to jump into become a Z boson. It's just going to be the same boson as it propagates. But in the case of, so When you have non-abelian gauge theory, I just told you that this is not allowed. It's not allowed. This you cannot take out. So you have to work with this determinant. This is highly non-local object. Hopefully that's clear. A way to make this local, write this locally, you just write it in terms of a bunch of anti-commuting fields called ghosts and anti-ghosts with such a local action. These are all made up, right? This is a path integral that gives you this determinant. Why do you do this? Again, because you want a local action. We invented unphysical gauge degrees of freedom because we want a local action. Here, the result of the change of variables inside the functional path integration, this gave us this determinant that because, again, we want to insist on local action, we write it this way, introducing ghosts and anti-ghosts. Good? This is something that came out of the path integral, functional path integral. So this is a purely quantum concept. So from this, hopefully you see that these are called the Fadeev Popov ghosts. They are scalar under Lorentz transformations, but they transform as they belong to the adjoint representation of the group. Think about why. Why are they in the adjoint of the group? Just expand this. Here's what it looks like. So what does it tell you? It tells you that C and C bar interact with the gauge field. So there's going to be a vertex. I've rescaled by factor of 1 over G. Once you go through this in your homework, you're going to see. Questions? This action will give you the following propagator for CC bar, which is just diagonal. They're massless, right? This is diagonal and massless. They're scalar, massless scalars in terms of the Lorentz indices, and they transform in the adjoint. So the full Lagrangian becomes this, minus a quarter f mu nu a squared minus 1 over 2 c del mu a mu nu of a squared. This is the arc C gauge thing. Psi bar I d slash minus m psi. This is charged matter. Plus C bar of A minus del mu d mu a c c c. This is the ghost anti-ghost coming from the determinant. All right, I'm going to pause here. Are there any questions about this Lagrangian density? We're done with Fadeev Popov. I'm going to repeat it next time as well. There were 2 steps. You split the path integral into the part that is gauge dependent and the gauge orbit. Right? The gauge orbit will just give you some extra divergences you're going to discard. Right? That's step 1. You're going to gauge fix using some omega. You're going to path integrate over omega with a weight that gives you the arc C gauge. When you impose the gauge condition, delta of G inside the path integral, you need to do you'll pick up a Jacobian from the transformation, from the fact that it has to be identity. And that Jacobian will give you a determinant that in non-abelian gauge theories linearly depends on the gauge field. Therefore, because you want to write it as something local, you write it as an integral over made up field called ghost anti-ghost with a vertex with the gauge field to just represent that delta. Good? All right, here's the action. What are the Feynman rules? Feynman rules for ghosts. This is the propagator. They interact with the gauge field, and the interaction is minus G F A B C P mu. How do you see that? This d mu expanded has a linear term in it, in A. There's del mu in it. That del mu will give you a derivative, P mu. Why FABC? Because they transform in the adjoint. All right. That's it. So in summary, we found that we find that arc C gauge in QED could be imposed by adding a term 1 over 2 C del mu A mu to a Lagrangian. We went through a derivation of this trick systematically and generalized it to non-abelian gauge theory. In Fadeev Popov, in addition to this step, we also average over, well, sorry, this step involves averaging over these gauge configurations, right? In non-abelian gauge theories, this averaging gives us this determinant thing. Sorry, not this averaging. In fact, the second step, which was this about this imposing the Dirac delta function, gives us this Jacobian, this term. This is not in abelian gauge theories. This is field independent. Just drops out of correlation functions completely, right? It's just an overall constant. We go to the right. In non-abelian gauge theory, it depends on the field. Therefore, we introduce ghost to represent this using a local term in the Lagrangian, in the action. All right? So this is what the Fadeev Popov for non-abelian gauge theory is. Questions? Next time, we're going to go through the quantization. But by now, you should know what is the matter content that you have. You have gauge bosons. Good. You have the fermion propagator. Well, fermion propagator. What else do you have? You have the interaction. You have the interaction with the boson, with the gauge field. You have a vertex for the boson, another vertex for the boson. You have the ghost, right? And you have this interaction of the ghost with mu. That's it. These are all the diagrams that we have. We're going to quantize this theory next time. We're going to compute the beta function and find it to be negative. Any questions? This is pure gauge theory, okay? Oh, no, sorry. Well, I jumped ahead of myself. This was charged matter field. These were charged matter fields, right? So pure gauge theory is that. This is pure gauge theory, not abelian gauge theory. Any other questions? Yeah.
So this ghost, this propagator, since it has a like one of C excited, it should be like the non-physical, right? So
absolutely not. Yes.
Something like the counter terms that's like helps in calculation.
Counter terms are, yeah, it's something that helps the calculation, yes, but not quite like counter terms. Counter terms are designed to cancel divergences. This is designed to keep track of our change of variable, or you want to say unitarity. It's designed to keep track of unitarity, if you wish. But it's just there because you want, the only reason it's there is that you insist on local action. If you could work with determinants, you know, it was fine. One more thing. Are these dimension count? These are the interactions, right? Forget about this for a second. These are the interactions. Pure gauge theory. Are these marginal, relevant, or irrelevant?
Marginal.
They're marginally 4 dimensions. So there's hope. All right. Thank you so much, guys.